Hello, everyone. I have really been looking forward to this webinar. I'm Susan Nash, AAPG, and I'm just thrilled because we are in the third of three wonderful geothermal focused webinars that have been supported by and sponsored by Halliburton and also endorsed by our geothermal committee of the Energy Minerals Division. And so super excited about it. And what makes this one different than the others is that we're talking about super hot rock as well as overcoming engineering issues that happen in geothermal. So it's incredibly forward-looking and also practical. So I'm really happy to introduce our speakers, but before I want to mention a few things. So for example, you will be getting a recording of this webinar in your email. You'll have a link to it, and that will come in a day or so. And also, if you have any questions at all, please look at the bottom and click on Q&A and add them to Q&A, and we will handle those at the end. And then finally, I just again want to say thank you to Halliburton. And at the end of the presentations, we'll just do a quick recap of the other two webinars, which are available on demand. So first of all, I'd like to introduce Pete Schiermeier, who's the Global Product Manager at Halliburton. He'll be going first. Then we have Gabrijel Grubac, who's Senior Completions Engineer, Mazama Energy. So I'd like to invite Pete to share a screen and to say welcome.
Thank you, Susan. So I'll start with a little bit more in-depth understanding of my background. So my name is Pete Schiermeier. I'm the Global Product Manager for Survey and Ranging Technologies within Halliburton, Sperry Drilling specifically. My presentation is going to be on magnetic ranging for geothermal applications. So this topic is, ranging is always it's a wormhole of information, right? So I want to really stay focused on geothermal applications, dive into really the basic concepts of ranging technologies, what you need to know to identify different technologies and what they do. And then we're going to apply those to geothermal applications, some new developments that we've had, but then also understand, really the arena that Halliburton is involved with in regards to low carbon solutions. So I wanted to thank everybody for calling in and appreciate your time, and let's get started. So traditionally, you think of Halliburton as an oil and gas company. We're very active in this environment, obviously, but we're also very active within low carbon solutions in a variety of scenarios. One being carbon storage or CCUS, hydrogen, direct lithium extraction, as well as geothermal. For this presentation in particular, we're going to be focusing on geothermal ranging technologies and the application to those technologies and different systems that we'll go into in the next slide here. So as you know, geothermal wells are evolving into more complex systems. There's a variety of different scenarios that you can deliver or different projects for geothermal applications. Your traditional geothermal is your vertical well scenarios where really you're drilling these wells off a directional survey and placing these wells based on survey understanding, getting into the formations of the rock, and then the natural fractures of those formation then gives that that exchange of fluids for the energy creation. Enhanced geothermal, EGS systems. This is where you're placing two wells. While you can do this with directional surveys, we'll go into a little more detail on this one. Directional surveys may not be the best option for you to accurately, place these wells to maximize the project's requirements. So EGS, again, spacing two wells in parallel, doing fracturing to recover some of the geothermal gradient in that area. Advanced geothermal systems, also known as AGS systems. This is where there's different scenarios for AGS systems that you've heard of, the Everloop, that's a trademark, Everloop systems, or even drilling. I view this as drilling an underground radiator and connecting the wells at the toes, toe to toe, or in an ever loop scenario, you're paralleling and connecting at the toes. But either way, that's a closed loop system where you're injecting obviously uh, cold water as an example, heating it up and getting energy creation from that. So EGS and AGS style wells is really where the ranging applications can be applied. And I want to touch on those very high level because we can go down the wormhole and I can confuse everybody on the call. So I don't want to do that. We'll just keep it high level and dive into those. So the last one is supercritical geothermal. So what we're trying to do here is you're taking these wells and then pushing them further down into those extreme depths and pressures and temperatures to really maximize, call it the energy return to give the best bang for the buck, if you will. So obviously with supercritical geothermal scenarios, there's always a ceiling with technology. So my background is technology development for the obvious survey and ranging technologies. And there's always a ceiling, right? There's always a temperature limitation or a pressure limitation with technologies. Once we start pushing the envelope of that, then you have to look at the technologies being applied downhole and how we improve that or evolve that technology to meet the needs of the customer's project. So once we start getting into the extreme heat, depth, pressures, that's where you have to look at what are you drilling this with, and does the BHA or technologies downhole survive these conditions? So again, we'll dive into the EGS and AGS style systems and as it's applicable to ranging technologies. Let's start at the basics. So why do we want to use magnetic ranging technologies? To be quite simple, surveys aren't enough. So surveys, the raw value, the surveys have what's called modeling. So you're given a survey, a point in space. A lot of times, you wouldn't believe it, but a lot of people that I talk to, they actually believe the surveys are exactly where the MD, Inc, and AS say they are. But what people don't know is based on the survey tool being used downhole, there's gyros, there's magnetometers, and there's different variations of magnetometers, sensors, etc. They're all survey equipment, right? But there's uncertainty associated with that spatial point that we're actually surveying that's unique to the survey tool itself. And what I mean by that is that's a modeling concept that produces what we call an error of ellipse, an EOU, also known as a tool code. That assigns uncertainty around that point in space that you believe you are within this space based on a confidence level, based on the center point measurement that the tool takes. So as you get inclination and azimuth movement with your wellbore, that tool code or EOU propagation gets larger and larger with depth, inclination, and azimuth change. So when you're getting into a horizontal and you're trying to parallel or pair these wells, there's a lot of ambiguity in where exactly they fall within this EOU, within this tool code. While you can still place wells that way, it's not a direct, exact correlation on where you are in your drilling well compared to your offset well. So why do we need to use ranging? Well, what ranging does is actually remove that uncertainty. It gives you a precise distance and direction measurement in relation from your drilling wellbore to the target well that you're trying to detect. It gives you that spatial separation as well as the alignment in relation to the target well. So that error of ellipse, that ambiguity in the tool code goes away, and it's actually based on the exact distance and direction measurement and accuracy of the ranging technology being used downhole at the time. Those are the specs of the tool. They're well understood within an accuracy margin with depth as you drill. So you don't have a propagation rate anymore. It's an exact space, a correlation with distance and direction from your drilling to your target well. So that's why we use magnetic ranging. What is magnetic ranging though? To summarize it very simply, what we're doing is generating a magnetic field. And then you want to detect that magnetic field. And there's different arrays, different variations of detection that we'll go into. And then once you detect that magnetic field, you can actually give a distance and direction target determination based on the reading of the technology being used downhole. And again, each technology has different accuracy levels, has different applications on how you need to run it. And these all have to be taken into account when you're planning your projects. and wanting to go into the implementation phase. So early understanding of project deliverables, what you can and can't do, and what's important needs to be understood when you're selecting arranging technology. So let's step through that chart that we just went through. We need to generate a magnetic field. So there's four main ways we can generate a magnetic field, and they're classified as active and passive sources, magnetic sources. So active sources means you're actually inducing a current on an apparatus, on the technology to produce the magnetic field. So it's a physical, you turn it on, turn it off, or you're doing an action to generate the magnetic field. Excuse me. The first one's current through a wire or on a pipe. The next one's current through a coil of a wire. The next one's permanent magnets, and we'll go into each one of these with technologies. And the last one's the remnant magnetic field of target tubulars. So you're using casing or the tubulars that are already existing downhole. So these first three are active magnetic ranging scenarios where you're producing the magnetic field. So again, you're inducing, you're doing an action to generate the magnetic field. It doesn't come just naturally. The last one is passive. That's where the existing casing or the tubulars have magnetic properties, and they just naturally induce a signal that you can detect and measure. So each one of these, again, are different technologies that we have within the Sperry fleet that we can optimize for geothermal applications. All right, so now that we've generated a magnetic field, how do we detect it? There's various ways of detecting the magnetic field. The first one is magnetometers, the one to the left. Magnetometers are common sensors used within measurement while drilling tools, so survey tools that are used downhole. The magnetometers can be contained within the drilling BHA, or they can be deployed via wireline to where you put them down the target well and they're not in the drilling BHA. But as long as you have the magnetometers coupled with a specific ranging technology, that will enable distance and detection measurement to be done after you detect the magnetic field that you're producing with the magnetometers. Gradiometers are another way of detection. So gradiometers has a set of sensors within the BHA. And what the gradiometers are actually doing is you've got a pre and post signal through magnetics that you're measuring the initial, call it pulse, and then the return signal that comes back is also measured through the gradiometers. And within that process, we can actually understand the distance and direction measurement from the drilling to the target well off of that signal. So again, the previous slide, I mentioned those four active and passive ways we generate a magnetic field. Those are technologies. Now going into this slide, how we detect the magnetic field further refines those technologies to a specific technology application. So it further refines and de-blurs your window to this is the technology specifically that we want to use based on how we're generating a magnetic field and how we're detecting the magnetic field. So ranging applications, there's a lot of them for ranging technologies. You want to do a well intersect or you want to miss a well, right? Or you want to do a combination of both. So for well intersections, typical applications are relief well, plug and abandon, or P&As. You want to do multiple intersections, intersect in vertical with the horizontal, connect end to end. We call that river crossing or open cased hole reentries. A lot of times we'll have subsidence where it breaks the well, the casing, so it cuts production off and we have to drill around it and re-enter into it later. Those are just examples of well intersections. Well avoidances or twinning. We see this in SAGD or frac recovery. SAGD is steam assisted gravity drainage. Our core SAGD market is in Canada. So when we say twinning, there's a lot of common overlap with EGS systems, EGS geothermal wells that are the same as what we do with SAGD. At the end of the day, we want to have that particular spacing for alignment when we're drilling these wells, and then making sure that the separation and alignment stays consistent for the entire life of the well. We want to see that within geothermal as well. So Sperry has thousands of wells that we've done SAGD. That's our bread and butter in Canada. We know what we're doing. We know how to do it and how to execute it. Now we just apply that to geothermal, and we have expertise in the field and in the office to do that planning. So that's just one area where there's a lot of overlap with geothermal. The rest for avoidance is infill drilling or redrills, pad optimization. So if your wells are spaced really tight on the pad, we can actually open it up with ranging applications further downhole where it clears AC issues or anti-collision issues. So that high congested, high density environment, you can navigate around wells and not hit them. So you use it for avoidance. Excuse me, I've got a tickle in my throat. Okay, so now we'll dive into the ranging technology itself, and I'll open up all these and just kind of start talking on them. So you see axis dependent ranging. What does that mean? So axis dependent ranging means you have access to the target well you want to range to. So you can physically deploy a tool down a target well to generate a magnetic field. You have that entrance on surface, if you will. So technology in that arena is MGT, or what's called the magnetic guidance tools. So this is where you have a target well, and then you have a drilling well, and in the target well, you deploy a wireline conveyed magnet, and you turn that magnet on and off with a power supply at surface. So as you're drilling these wells, let me get this right on the picture, you have a MGT in the upper well, you pre-position that, and then as you're drilling the lower well, you stop, turn on the MGT, make a reading with your MWD, your magnetometers, and then you do a distance and direction measurement off of that, start drilling again, and then either pump or push that MGT to the next point, and you just continually do that. So that's what MGT is. Again, the magnetic guidance tool. MGT will come back to here in a few more slides, so keep that one in the back of your mind. RMRS is the rotating magnet ranging service or system. This is where we're taking rare earth magnets and putting it into a collar and rotating that collar. So for RMRS, what we're doing is actually placing the magnets in the drilling BHA, and then in the target well, we're deploying an MWD, basically an MWD tool via wireline, pre-positioning it in the target well, and then as we drill, as we drill the well, we rotate the BHA and it produces a magnetic signature, and you detect that with the MWD tool that's on wireline on the reference target well. So you can either do parallel alignment, you can do a cross by where you can detect the well. And there's a lot of different applications with RMRS technology, but essentially what you're doing is taking rare earth magnets, putting it in a collar or a sub, rotating that sub to generate a magnetic field based on the magnets in it, and then detecting that magnetic field with magnetometers in an MWD tool deployed via wireline. And then similar to MGT, you pre-position the MWD tool as you drill by it with the RMRS tool to detect it, the drilling well. You get a distance and direction measurement. That tool keeps drilling, and then you push the tool to the MWD tool to the next survey spot. That's RMRS. SWG is single wire guidance. So this is taking a power line essentially and putting it all the way down the well. So the assumption is you can put a line all the way down the entire wellbore in the target well, and you energize that line on surface, and then you detect that with your tool in the drilling well. So that's another application of axis dependent ranging technology. So MGT, RMRS, SWG. The other ranging technology that we have is what we call axis independent ranging. This one's really important to understand because now you don't have access to the target well. So you have a blowout, or you have a collapsed casing where you physically can't put anything down the down the target well. So well spot is our primary well intercept tool. So this tool gives us the capability of identifying well accuracy within sub inches. So this is a high precision measurement on bottom of the open rat hole, truly on bottom, to give us an understanding where we are in relation from the drilling well bore to the target well. So well spot Nothing's in the target well. It's just a well casing that's out there somewhere. As you're drilling, you trip the BHA out, come back in with this wireline tool, and there's a transmitter and receiver in this wireline tool. The transmitter induces current into formation. It collects along the target wellbore and then sends a signal, call it a signal back. And then gradiometers detect that signal and derive a distance and direction measurement off of that. So gradiometers, magnetometers, right, I mentioned before, help specify what technology you would be using. These are examples of gradiometers for well spot. So that induces a signal, collects along the target tubular, comes back, you detect it, distance and direction measurement identified with that type of signal. And then you trip that tool out, come back in with the drilling BHA, continue on, wash, rinse, and repeat that sequence. That's well spot. Aurora. So Aurora is, we used to use MGT for SAG-D as the primary method. Now we use Aurora. So Aurora actually clamps to the surface wellhead. And as long as you have connection with casing, it induces a current along the casing of the well. And you detect that casing with what's called the Aurora sub that's in the drilling BHA. The Aurora sub itself has a circular array of magnetometers that detect the current, the signature coming off of the casing. So all you do is simply drill to the point you want to do a ranging intersect, turn that target well on, energizes the target well, and you make a distance and direction measurement off of that. Turn off the target well just for HSE purposes on surface. Keep drilling and wash, rinse, and repeat that procedure for the whole well. So these are access independent ranging technologies where you don't have access to the target well, where you just have the drilling wellbore being used for ranging. Okay, so let's start kind of migrating in to new technology and where we were focusing on for geothermal applications. So our newest geothermal ranging tool that we focused on development that we're currently ready to deploy is what's called the geothermal ranging tool. So this tool is unique in the sense it has a receiver and a transmitter, but you have two wells drilling at the same time. I mentioned Everloops. Again, those are trademark ways Ever drills their wells for underground, basically these radiator systems. So if you, in that scenario where you have two wells drilling at the same time, you're going parallel and then you're intersecting at the toe, this tool does that. Or if you have two wells that are drilling at the same time and you want to drill toe to toe, this tool does that. So what we've done is focus on leverage off of proven platforms that we know how they work. They're robust. We're confident with any formation that we drill in. That's what we focused on with this tool. So if anybody's ever developed a new technology, time is never your friend. So when you're developing it from scratch, it takes forever to validate the tool works. Then in what formation? How does the data look? And then just proving that with reports and downhole data takes a lot of time. What we did with this application is actually leverage existing platforms for the receiver and transmitter that are proven designs, that technologies that we use every day. So the receiver you see is what we call the base star. This is the latest and greatest survey, call it survey tool, survey platform that Sperry has. We run it everywhere globally. This is a standard technology that we have within our fleet, and we pulled that off the shelf and said, God, can we make this work with ranging without changing anything substantially mechanically on it, right? And come to find out, we could use it. So that's what we selected for the receiver. For the transmitter, what we did was the transmitter generates a magnetic field. So what's the most efficient way that doesn't cause drilling condition issues to generate a magnetic field? Well, that was the MGT tool. So the MGT tool traditionally is deployed via wireline and we energize it. What we did with this tool for the transmitter is we took the MGT tool technology and actually power it with downhole generators. So it's contained within the BHA. We fire it up when we want it, we turn it off and continue drilling. There's no tripping of wireline or BHAs at all with this technology. So getting back to my point, we're leveraging off of proven robust systems that are quick to market, that are proven, and we don't have to really go down the long verification route of what you would traditionally do with new technologies. Excuse me. So this is the geothermal ranging tool. To add some more content behind that, this tool is, again, typically used for AGS style scenarios. We wanted to focus on improved well placement, so that detection range is extremely critical with geothermal systems. You want to have that maximum separation for that geothermal gradient, because essentially what you're doing is maximizing the spacing for the formation to regenerate the heat. You don't want it too close. You want it at a certain length. There's an engineered design for spacing that you want to achieve. Traditionally, with legacy ranging technology, specifically MGT, our detection range is around 30 meters. This tool allows us greater than 100 meters. We've done testing up to 130 meters with success. So this is an industry first for detection range, which gives you early understanding for alignment, any reaction to adjustments to those alignments, and then you're not depending on those surveys themselves, right? It's the ranging detection that places the well. We wanted to reduce ranging flat time. It takes us less than 10 minutes to do a full ranging determination, distance, direction, move on. So 10 minutes or less is very fast for the ranging industry in particular. We eliminated the wireline and unnecessary trips for BHAs. If you don't use this system that's fully contained, fully powered within one BHA for both the receiver and transmitter, you have to use alternative systems, so rotating systems. And some of those rotating systems are only good for a certain distance. So if you want to parallel and intersect, you may have to trip the BHA out. Also, rotating systems cause pole issues. Constantly rotating to generate a magnetic field can lead to problems. We don't have to do all of that, and we knew that going into it because of our background with the extensive ranging runs that we've done. We know what we're doing, we know what the problems are, what's the most efficient system we can design. That's what we came out with. So we focused on elimination of wireline and unnecessary trips. And then this system improves drilling performance and enhances the wellbore understandings with the offerings that our BaseStar platform provides. So BaseStar is not only survey, gives ultra high definition ultrasonic imaging, advanced pressure, and real-time drilling dynamics, WOB-TOB. So it's a very complementary solution for other service needs in the geothermal space. So again, this is the geothermal ranging tool that we just came out with, just developed specifically looking at AGS systems. I want to hit upon the distance of detection. So one of the byproducts that we found with this technology is it actually opened the door for EGS style drilling for ranging technologies with this distance of direction of 100 meters. That opens the door to where we did with a simple firmware, software, and frequency change that we applied with this AGS technology. We can now take that technology and apply it to EGS systems for detection. And that's what I'm going to go into with this case study. So we had a customer where they were drilling in granite. They wanted to maintain 215-foot separation, high temperature. They wanted to maintain that extreme separation distance. By the breakthroughs we had with the AGS, the geothermal ranging system, we actually applied that to the wireline gyro now and extended that range from 30 meters to a greater than 100 meters now, which enabled this customer to have that early detection of separation, not drill the well off of surveys anymore, but off of the ranging accuracy. And actually, we achieved 243-foot separation, maintained that with the combination of that wireline MGT improvement that we had a breakthrough with, and the BaseStar directional module. So this opened the door for other geothermal applications. So we're always thinking, how can we improve the assets for our customers' projects and give them more benefit? We're always looking at that. And this is just one scenario where it opened the door for EGS, an EGS solution. So this is my last slide. So Halliburton's been in the low carbon solutions for 70 years. We have advanced knowledge in different areas. And we just want you to understand that we've done everything from preliminary survey, exploration, field development, engineering and construction. We worked with the drilling vendor or the construction vendors on that front to operation and maintenance. So we have extensive bench strength within the low carbon solution environment, and we've been doing it for a long time, where traditionally you really wouldn't think Halliburton would dabble in this space. We have, and we have an extensive background in that. So please reach out to us if you have any questions. We're here to help. We want to be your trusted solutions advisor in any aspect. So we're here for you, and we look forward to your questions. So with that, I'd like to hand that over to Gabriel, the presentation over to Gabriel, where he's going to go into Mazama Energy's EGS style project. And with that, I'll hand it over to him. Thank you for your time.
Thank you, Pete. Thank you everyone for being here today. Before I step right into it, I wanted to thank AAPG and Halliburton for making this possible and enabling an opportunity to share with the world some of the let's say breakthroughs that have occurred lately. My name is Gabrijel Grubac. I am a senior completion engineer with Mazama Energy, and I am looking forward to walk you through a brief story of how we reached 331C this year and what that could mean for the future of super hot rock. And so, for the communities out there that have been in the oil and gas for a while, high temperature wells are typically in the range of 150 to 200 degrees. Once we step into the geothermal world, things are changing. We're now harnessing heat, wanting the ability to utilize that heat for power production. And 331C is essentially a number that has defined this year in terms of the technical challenges and the technical achievements that have occurred within our project. 629F for those that are not familiar with the Celsius numbers. Now, what this really meant for us is we were able to create the hottest EGS pilot in the world at Newberry, Oregon. And so essentially, the idea was to engineer a reservoir, to create a reservoir, a surface area of harnessing the heat. And how did we do that? We had an injection well that was one of the wells that has been drilled in the past that was recompleted. And so that was completed about a year ago. And then we stimulated the injection well. We're able to precisely drill the production well and place it almost within 6 feet of where we wanted it to be in order to have a system that could communicate. If you're looking at the numbers, we could look at the ROPs, an average of 72 feet per hour. What we thought was the leading challenge within EGS and drilling being the main driver is something that we have learned that it has its space, but the completion world is also now taking a big area in sense of the challenge itself and in the sense of economics, where drilling is not anymore just the leading factor, and we will have to pay a lot closer attention to completion. We have managed to retrieve a core, a 300 degrees C, a 12-foot core, and we're very excited. We've taken that to the laboratories. We're running multiple tests on it, trying to learn a lot about the type of rocks and different lithologies, because essentially we were in basalt, granodiorite, andesite, so we had the ability to get a sense of behavior of these kind of rocks under the conditions that we were working at. Zero NWD and motor failures downhole. You think of these temperatures and temperature management during the process, and we felt pretty good about this, as it paves the way for the future to reach supercritical temperatures. And most importantly, we've stimulated the wells. We're able to drill precisely, but recently have managed, to bring out and confirm that we have established a physical connection between the fractures and achieve the circulation, which is currently underway. And what this could mean for the future of EGS and super hot rock, it has huge implications because of the ability to harness hotter temperatures, the ability to convert thermal energy into electrical and essentially produce power, and maybe just one day become competitive with hydrocarbon-based power production. So 331C was achieved, and the question is how. And one of the big things that I would like to bring up here is the strong collaboration with all of the strategic partners that we had through this project, including Halliburton. The amount of communication that needed to happen and preparation to make this happen was considerable, and it wouldn't have been possible if we hadn't worked together. So we can drill these temperatures and creating a system that communicates, not a stimulated reservoir volume. I'm not a fan of that word, more of an engineered reservoir volume, because essentially we need a fracture system that can continue talking and communicating for extended times, and it needs to do that efficiently. And so one of the big things that we have applied in our project is the thermal lattice reservoir creation method. You can search for the paper out there. There's a publication out there about this method, but essentially the ability to take the work that we've done in the lab, so the samples that we have collected, and try to understand the behavior of the rock under these conditions, and being able to superimpose that on the field, which was very exciting when we were doing this, because we were trying to understand from a micro scale to a macro scale, what was that looking like and what did that mean. And we had physical tests, injection tests, our ability to diagnose the pressure behavior and understand the changes in transmissivity. And now we see a system that is capable to talk a lot more efficiently, not just from a tensile fracture itself, but a combination of it all, creating a lattice that can circulate fluid and harness heat. What you see on this picture is the beautiful site of the Newberry volcano in Oregon. And I must say that performing the stimulations during the winter months was a big challenge. For those that have worked in North Dakota and Wyoming and other cold places, I know this might be very common to you, but getting on top of that mountain and being able to move all the equipment and being able to handle the temperature changes, and the challenges with utilizing the fluid and pumping the hole, it definitely was a test. And that test came with a lot of planning, pre-planning, understanding what the logistics side of things meant, what did we need to prepare for ahead of time, the meetings that we needed to have to mitigate any of the challenges that will come from being in a remote area, because this is not the Permian Basin, and this is not a place that everything is readily available. I will briefly walk you through the injector well stimulation. What you're seeing on this slide in here is essentially a bit of a geological model trying to explain what type of rock we're dealing with. There's a temperature range in here and a depth range, so about 3,000 meters, 10,000 feet. Newberry does have the advantage of having high temperatures at shallower depths. And so we were able to tap into those temperatures back in the day when this well was drilled, but we had to run in and recomplete the well for what the plan was in terms of stimulation. And so, one of the big concerns when it comes to EGS, even from the past, has been induced seismicity. And one of the big wins, I would say, and that green color that you see on the traffic light, is that throughout this whole process of stimulation, we have detected multiple events that were in the negative range of magnitudes. We had systems that were run by Lawrence Berkeley National Lab, Pacific Northwest Seismic Network, USGS, and essentially a plan in the field of what we needed to do in case we saw any kind of magnitudes that were increasing, and what was the operation sequence and that everybody had to be aware of. We paid extremely high attention to this, wanted to make sure that the whole team was ready. What we were able to see with the fiber data as well, and incorporating all the data, is understand what the fracture orientations might look like for later placement of laterals, but most importantly, be able to see that no events with the greater magnitude of 0 we're seeing, and so essentially carrying out safe operations with this EGS project. And so what you see on the picture here is essentially a layout during the stimulation work. It was a challenging re-entry into this well. There were two liners, slotted liners in the hole. We were able to pull out one of the 7-inch slotted liners. And so we ran in a hole a 4.5-inch and a 7-inch and cemented that. So essentially you had a 4.5-inch cement 7-inch slotted liner and the rock at a 19-degree deviation, which for every stimulation engineer out there tends to be a good reason to lose sleep over. And the challenge was, the ability to create a connection between the wellbore and the reservoir, taking into consideration the high temperatures. And so what we had is a hybrid setup on the field with a conventional stimulation spread, with a coiled tubing spread, and the ability to run in hole with jetting BHAs, use abrasive perforating to create that connection with the wellbore, and then utilize the fiber that was permanently installed, that still up to date, is functioning, which has given us tremendous value through the projects, because what we were able to understand is the cooling and the heating cycles of the work that we were doing, and essentially real time make decisions on adjusting on how we're completing the well. And so what Mazama has been able to do through that process is the ability to apply wireline based perforating and utilize composite plugs for isolation. So it was a journey from it is very hot downhole. This is what we can do at this time, and we did it efficiently. And then understood that we had certain windows that we could work with, and so moved on into wireline perforating, setting composite plugs for isolation. And then that was an evolution from the injector side to the producer side. At this time, the producer has been drilled, stimulated, we have connected and circulated. But what we did is take all the learnings from the injector side, transpose it on the producer side, and that included also the application of the world's first sleeve at these kind of temperatures and the ability to open it and stimulate through it, or the application of hybrid stimulation fluids, something that maybe in the past was not thought very possible, but the ability to use high viscosity friction reducers and crosslink systems to generate geometry. And so that picture has been built, and we're building onto it as the ongoing testing is happening right now. And we're hoping that in the coming months we'll be able to share more with the technical community out there with all the findings of this proof of concept project. What you see on the left is a pumping plot with a pressure, a rate, and the reason why I might have lost a couple of years of my life. One of the very first stages that were pumped in challenging settings and basaltic rock. On the right side, you see a stage that was completed in granodiorite, a lot more, let's say, in that case, forgiving. Essentially, the idea is we had different lithologies. We expect a different kind of fracture propagation and height and length. What would that communication look like? And what are all the learnings that we can harness through this? So this is all being digested, applied in the producer well, and we're now, having a full picture and really moving forward strongly towards that next step into getting into the supercritical realm, which at this point is about 45 degrees away in Celsius from what we have just done. Now, in order to create a durable reservoir with fracturing, there is the utilization of proppants. And we were able to test different kind of proppants in this well, from natural sands all the way to ceramic. And the one thing that should stay with the audience is there's a loss of conductivity through time. There's a stress effect on the conductivity itself. And so now we're thinking, what will it take to achieve a fracture health index that allows us to circulate in an EGS and supercritical conditions and enable longevity. And that is one of the reasons I have this on the slides, is the economics of these kind of projects are taking us to 20, 30 years. And if you're thinking of 20, 30 years of circulation, there's a lot of thought process to be put into the ability to create that surface area, not just stimulate it, but engineer it with the thermal lattice approach that we have, the ability to apply the proppants and put all that together so that it technically works, but economically as well. Because once you start putting the numbers together, you start realizing that the completion costs might start getting really close to what the drilling costs might be, and how do we get these economics to be better for the future. At this time, with what has been completed, with all the work, with the ongoing lab testing, working on the course, the ability to build that picture, moving forward, I did remember an anecdote I wanted to tell you is once that core has been retrieved on surface, I had shown up on the site location and I wanted to take a look at the cores because who wouldn't want to see something from 10,000 feet deep at 300 degrees C? And one thing we noticed is the presence of proppant. And so what that really told us from a stimulation perspective is an exciting proof that we had physical transport of proppant at those distances, that we were able to connect these fractures that later enabled us to circulate through the whole system. What you see on this slide is essentially what the plan is moving forward. In 2026, Mazama will be diving into the demonstration of 400 degree C drilling capability. And with that will come a lot of, I will say, a lot of great scientific excitement. And on the other hand, a 15 megawatt commercial pilot. Now that we have done a proof of concept project, learned a lot, taking all the learnings, building onto them, and the ability to drill 2 horizontal wells in the coming year that will get us into the super hot zone, stimulate them, connect them, and be able to produce power that will hopefully pave the way for a future of cleaner power production coming from geothermal. That would be all for my end for today, and thank you everybody for being here.
Well, thank you very much. I really appreciate it. And we have a number of highly rated questions as well as ones that haven't been rated yet. So anyway, I want to mention before we get into the questions that this is the third of 3 Halliburton focused webinars, and the first one was enhanced geothermal systems. The second was engineering considerations and challenges, and that included a case study of Fervo and their work in Utah, and also then today is geothermal innovations in action, and we have just so much to talk about. Then I also like to mention that we have an upcoming in-person event in Houston, and it has a lot of focus on geothermal, subsurface energy to power, where we talk about going all the way from reservoir characterization to what it takes to actually generate the power, and then looking at things like data centers and cooling demand as the and communities grow, etc. So this is exciting. It's the 7th and 8th of January. Please check out our website for details. And you can also always contact me as well. So anyway, I'd like to go ahead and start the questions. So if you have a question, please go ahead and put it in the Q&A and type it up. We won't be answering anything. We won't be talking to any of the participants live, but would like to start with this question. Do different casing materials affect the induced magnetic fields, or how are they detected?
Yeah, Susan, thank you for the question. So yes, they do, and it really depends on what ranging technology you're looking at. So are you using passive magnetic ranging where you're trying to detect an existing tubular casing? If that casing's deteriorated or extremely old, brand new, gives a different magnetic signature, obviously. So casing understanding is very important in a PMR application. Also comes into play with axis independent ranging technologies. It's something that we definitely take into account along with the formation, obviously, and we model that. So that's a call it a pre-planned scenario where we get all the understanding of the target well, where it's being drilled, what formation, and how that affects the signal, to accurately basically chart out success, probability of success with that ranging project. So yes, casing needs to be understood. But remember, the geothermal ranging technology that I described, you're not necessarily detecting casing. So in that scenario, you're detecting the next drilling wellbore, the direct magnetic signature that it's creating. So casing doesn't come into play in that scenario. So it's only when you're trying to detect a casing, or you're deploying something to ping off of the casing, if you will, that you need to bring it into play.
That's really, really interesting and a great answer. It does remind me of that Halliburton has so many years of experience. Did you say 70 years in geothermal? That's amazing.
Yeah.
That's great. Okay, so we have another question that just slipped away because it moved. Okay. What type of temperature tolerances are achieved for these ranging technologies? In other words, will they be suitable for super hot geothermal, or will additional developments be needed?
Yeah, no, that's a good question, because when we're utilizing the geothermal ranging technology that we have, it's limited to, you know, the lowest thing in the BHA that's being deployed downhole, right? So right now the geothermal ranging technology is limited to 160 degrees C. That you can use mud chillers, insulated drill pipe, et cetera, that we've used historically to bring those temperatures down. But right now it's limited to that, and that's directly linked to the Baystar tool itself. So when you start exceeding that stuff, you know, Halliburton Sperry has what's called solar tools that are in that 200 degree C stuff, but everything else has to survive within that environment. So not only are you looking at the survey technology, but everything else related to that drill string, will it survive those temperatures? So you have to take that into account as well. As you go into these superheated environments, I think the industry, you know, you need to look at upgrading the platforms and what's the necessity platforms or the required platforms to drill your wells, and can it go beyond 200 to 300 degrees C, right? You have to assess that information, because it's technology advancement that you're going to have to do, and there's a lot of work that has to go into that.
That makes sense. Okay, so I've got another question, and again, it moved. My Q&A keeps slipping around. Okay, so Luis Chabot says, thank you, Pete, for the presentation. What geological subsurface conditions can impact the accuracy of ranging systems? Sandstone containing disseminated pyrite, and the okay, well, the question just disappeared. So anyway, I think it must have been.
I can take that. So
Okay.
yet another great question.
Okay,
So
here's
that,
a highly resistive shale was the other one. Okay.
yeah, at the end of the day, with the geothermal ranging technology that we developed, we're finding that formation doesn't have an effect on the signal. So early on, when we built this tool, we did what's called a surface test. So you lay the physical tool out on surface. You want to identify the maximum detection range within an accuracy margin, and you're physically putting it on the surface and firing it up. So we did that. You can calibrate for formation. You can calibrate for casing that you're inducing the field through, to back all these components out, right? So when we did our field analysis test, if you will, we came up with accuracy values that we know what not drilling through formation looked like, to keep it simple. And then when we actually went down into the ground drilling, what we saw was an echo of what we saw on surface downhole in deep depths. So and then we went on to that case study in particular was drilled in granite formation. We didn't see any attenuation of the accuracy signal there either. So what we're seeing is downhole data that verifies and matches what we saw at surface. And so far, the wells that we've drilled with this tool, we're not seeing any effect with this particular combination of technologies due to formation.
Okay, thank you. Well, we have some highly rated questions too for Gabriel. So, Gabriel, how long will a geothermal project such as Newberry be expected to produce usable heat? I know that probably there are some questions you can't answer, so feel free to let us know.
No, thank you, Susan. That's a great question. I'd like to make it clear because I've been reading some of the questions. Just to clarify, the current project that was completed was a proof of concept. So really, what the goal behind this was to de-risk the technology for super hot rock, rather than achieving, flow rates that can produce power, even with the setting that we were in, because the goal for the future is to drill horizontal wells and then produce out of those. In terms of how long will these projects take, this is something that we're working on right now. But essentially, it goes back to what I said earlier during the presentation. These projects are looking at 20 to 30 years viability. And in order to achieve that, we have quite some technical challenges that we need to get through. And one of them being mostly the longevity of the system that you have created, essentially those fractures that you have connected.
Excellent. Okay, so we have another highly rated question. Are formation losses an issue in enhanced geothermal system reservoirs? And if they happen, how do you mitigate this? And are there specific completion designs to solve this?
That is a great question. Yes, it is a challenge. No matter what AGS you will find yourself in, I believe it's a myth when sometimes you hear there's this big chunk of impermeable rock that is not realistic and it doesn't depict reality. There is losses. The question will be how much of that is losses and how much of that can be made up. In terms from a completion standpoint, what we can work on is the distribution of fluid through these fractures for harvesting the heat. But what the loss in the secondary system is, there is certain solutions to that, but that still needs to be worked on. I think what is critical for the audience to remember is the ability to go to super hot with a higher enthalpy essentially means us being able to use less water than you would at a regular EGS at lower temperatures. And I think this is one of the big advantages because there will be places where we can apply the same technology where water won't be as available, and we need to be mindful of this.
Excellent. Okay, here's another question. Did you observe a natural connection between the wells before stimulation?
That is also a great question. I think it came from Eva. No, we did not. What we have observed is the presence of propan in the core. But that kind of natural connection at that point, no. Once we started doing the diagnostic stats, we started learning a lot more, and we really hope to share this data more in the coming months as we're building a full picture of all the learnings that we've gotten through the process.
That's good. Excellent. Well, there's so many questions. We have time maybe for one more. Let me go to, uh, okay, so another question. How is subsurface characterized on a regional scale? Temperature and pressure.
Yeah, that's also a great question. I mean, Newberry is not something that just came out of the blue. It's been there for a while. There's been a lot of work that was done in the past um, from other parties that were involved in this kind of project. So a lot of the modeling, the temperature modeling, had been done in the area with some geophysical methods as well. One of the big things that we're also working now is refining and recalibrating these models based on the latest data. So pressure available from what we have seen during the drilling and the stimulation. So essentially physical measurements, and now we know what that distribution looks like. Temperature has been known in the area. Now we have a lot more physical data to use. And so, working on the thermal model and understanding better as we move forward, how close we are to that realistic number of what is the depth that we need to reach for super hot rock. So
Well, we have many questions that we couldn't get to, so I just would like to encourage people to send an email directly to APG Education, and we'll pass along the questions. And also feel free to get in touch directly with Pete and Gabriel. So thank you very much. I see lots of accolades, hand claps, and hearts and coming up. And so I want to thank you again. And also just a final thank you to Halliburton for this wonderful three-part series that are all available on demand, and you will get an email with a link to the recording for this one. If you've missed the first two and you can't find where to register for them on demand, email us also. So thank you again, and very, very much appreciate it.